So, today finally we have reached a very important moment in this course. And I'm glad to say that we can start today the third and what is to me the most interesting part of the course. So we have laid the foundations with several examples of dynamical systems and the notion of topological conjugacy. And now we are ready to take a fresh look at the orbits, at some of the fundamental concepts from a slightly different perspective. And we're going to look at the same objects that we have become familiar with now, but we're going to use a slightly different language, and this is going to open up a completely new direction of investigation. So let's start back. Let's take a few steps back right from the very beginning of the course. If you remember, we started with a really basic setup when X was a set. I'm now going to assume that X is a metric space because that's what allows us to formulate many of our concepts. So this is a metric space X. Then we have some map F from X to X. And if you remember, the very starting point was, okay, this determines a dynamical system in the sense that if we take some initial condition x0, it determines the orbit, some orbit. So we defined the concept of a forward orbit initially, and then if it's invertible, we can define the full orbit. Xn is just the iterate Fn. So as we explored the different ways, as I said in the beginning, the object, really the fundamental objective of dynamical system is given a map like this to describe the structure of the orbit. We've seen a variety of different examples. We've seen that even in very simple one-dimensional setting, you can have a whole bunch of crazy behaviors of this, right? And you can have lots of different kinds of orbits. So what do I mean by taking a different perspective? Now we're still going to work exactly with the same objects. Our objective is still to describe this orbit, but we're going to use the language of measure theory to do that, right? Measures. So we're going to try to describe the structure of orbits with measures. So X is a metric space, so in particular it's a measurable space. So we can define measures on this. So how do we describe the structure of the orbit with measures? What does it mean? It means I want to put a measure, a probability measure, right? So I presume that you have studied in the concept, the definition of a probability measure in your real analysis course, I imagine. You studied Lebesgue measure. I presume did also more general probability measures. We're not going to need that much theory about probability measures. A little bit. If you need a little bit more background, maybe you can discuss it with Doug in the tutorials. But we want somehow to put a measure, a probability measure. Probability measure means a measure where the measure of the whole space is 1, right? So a finite measure. And we want to somehow describe this orbit with a measure. So the way I imagine measures, I think a very good mental image of a probability measure is that you have 1 kilogram of sand, right? And you take this 1 kilogram of sand, which is your measure 1, and you kind of spread it out in your space, right? And that gives you the different measure of the set. So when you take some set A and you want to know what the measure of this set A, it depends on how much sand you put on this set A and how much is everywhere else, right? This is the measure. We will see several examples of measures. So we want to put a measure on the orbit, right? Because we want to use this, we want to have a probability measure that somehow reflects the position of points on the orbits, or somehow describes the orbits. So how can we do that? Well, there's one simple example. If x0 is a fixed point, so if you have or let's say we have a fixed point P. So if P is a fixed point, right, then the orbit of P is just a point P. It's just a single point. So there's not much to describe. What we want to describe is just a single point. I want to say this orbit is just a single point. How can we describe that with measures? You know, how do we put a measure, put our 1 kilogram of sand just sitting on this single point?
Dirac measure, Dirac.
Exactly, right? So we can define what's called the Dirac measure. It's denoted by delta P. This is sometimes called the Dirac delta measure. And the Dirac measure is a measure on the point P, right? And the formal definition of this measure, if you take any set A, right, this is a measure, so we can take any measurable subset, and we ask what is the measure of this subset, and the measure of this subset just depends on whether this subset contains the point P, right? So the subset is 1 if P belongs to A, and 0 if P does not belong to A. This is called the Dirac delta measure in P. It's one of the simplest examples of probability measures. It corresponds to putting all the mass, all the weight, all the sand on this single point. So if I give you a Dirac delta measure on a point P, then this measure identifies the point P, right? Because all the measure, when you look at your space, with that measure, the measure you can also think of as a kind of lens or telescope, right? Or the way that you're looking at the system. I look at the system, but what I see is where this measure is, right? And if I give you the delta P measure, then it is sitting on P, and basically that's the only thing I see in my space, okay? And so I'm telling you that the orbit of P is described by the Dirac delta in P because the orbit is just a single point P. Okay? What's the natural generalization? Suppose we have a periodic point. Then again, it's quite easy, right? So we just have the orbit, the forward orbit. So if P, P1, P2 is a periodic orbit of period 2. Let me generalize a little bit. So let's just have P1 to Pn, right? Periodic orbit of period n. So that P1 maps to P2, P2 maps to P3, and so on. So P2 maps to P3, P3 maps to P4, and then you go back to P1, so you have a periodic orbit. Then we can easily generalize this Dirac delta, right? So what we really want is, again, we want to describe these endpoints using a measure, a probability measure. So the obvious thing to do would be to put just a Dirac delta on these, but we only have 1 kilogram of sand. We don't have n kilograms of sand. We just have a probability measure. So we just divide it in equal parts on the orbit, right? So we define a measure mu to be equal to 1 over n delta P1 plus 1 over n delta Pn, right? Or I can write it as 1 over n, the sum of delta Pi, I equals 1 to n. This is now still a probability measure, right? So if I take a set A, right, what is going to be the measure of the set A according to this measure? So what I've done here is I have put a fraction, I have distributed my 1 kilogram of sand equally on all the points of the orbit, right? So on P1, I have 1 over n of the measure. On each point, I have 1 over n of the measure. So you can see that the measure of a set A is just exactly the sum of this, right? So this measure of a set A is equal to 1 over n delta P1 of A plus so on 1 over n delta Pn of A, right? So in each case, this value is either 0 or 1, depending on whether P1 belongs to A or not, right? So this will be exactly equal to some number, let's say k over n, right? Where k is exactly the number of points that belong to the set A. So the measure of A will be if there's, in this case, there's just 1 point, so the measure of A according to this measure will be 1 over 4, right? 1/4. If we take a set A that contains the full periodic orbit, then the measure of that set will be 1, right? Because I am taking my probability measure, I'm distributing it equally on the periodic points. Is that clear so far? Are there any questions? Okay. And remember, what did we do? So we went through exactly a similar kind of steps right at the very beginning. You know, we said, okay, if we have, when we were looking at dynamical systems from a topological point of view, we said, okay, if you have a fixed point, it's a fixed point. If you have a periodic orbit, if you have a periodic orbit, but what if the orbit is not periodic? What if it consists of an infinite number of points? How do we generalize this measure? How do we put this, how do we spread out this probability measure on an infinite number of points? Right? So what if the orbit of x0 is infinite? How do we describe it? Can we describe it using a probability measure? What do you think?
Average weakly converges to some measure. These averages of Dirac measures.
Right. So the problem here is that you cannot really do that. You cannot really put a measure on the infinite orbit, right? In any way that is immediately obvious, because if the orbit is a countable set, certainly you cannot distribute it, put a measure in a way that gives the same weight to every point, right? Because even if it's an infinite set, even if you put a tiny, tiny measure epsilon on this, you add up the total sum of the measures will be epsilon, right? You cannot divide by n here. If you put some epsilon measure on each one, then the sum will be infinite, which does not give you a probability measure. So in principle, we could try to put, you could try to put, if you really were trying to do this from scratch, you could put some kind of converging sequence of weights, right? You could put half measure here, 1/4 here, 1/8 here, 1/16 here, right? But it's not clear what the logic of that be. Why would this point here be worth 1/16 of this? It also depends how much you want to weight, the initial pieces of the orbits compared to the further pieces of the orbit. Is not a consistent way. Also, if we start with this initial condition instead of this, then we would get different weights for the different things. So, as Milmukshin said correctly, the one thing we can do is look at finite pieces of orbit and look in some way at the limits in some way, right? Which I will describe in a second. So also in the topological, when we looked at this from a topological point of view, if you remember, we did not actually, we found a solution which was through the omega limit set, right? Which does not really describe the full orbit of x naught, but it describes the limit points of the orbit. So it describes where the orbit ends up after a long time, right? So in some sense, if we cannot describe completely the orbit, we at least can say, okay, where do the points of the orbit end up somehow, right? That was the topological omega limit set. Now we're going to do something very similar, but also very different, as you shall see. Okay, so the analogy with the omega limit set is important and it's correct, but as we shall see, there are many differences between how we're going to describe them now. So what we can do is we define a family of measures. So we define a sequence of measures. Of probability measures. Like this. So let's define the sequence mu n. Each one is a probability measure, and it depends on the initial condition x0. So we choose some initial condition, and then for each n, we take exactly this, this average. Right, where xi, of course, is the iterate fi of x naught, as usual. So this measure in itself does not have much meaning. This measure, so let's forget about these periodic orbits that we have here. So you can see that for n equals 0, for n equals 0, well, for n equals 0 is not quite defined, okay? Let's say for n equals 1, the indexing is not exactly right here, but for n equals 1, yes, for n equals 1, we have just delta in x naught, right? So what does this give us? For n equals 1, we have mu1 of x naught is just delta of x naught, right? Because this is n equals 1, this is 0, so this is just delta x naught. So this is a measure, sorry, I have to jump back and forth. This is just the Dirac delta on x0. Now the Dirac delta on x0 is not particularly interesting because this orbit is soon going to move away from x0. So then we define another measure, which is for n equals 2. We have mu2 of x0. And now we divide equally in these two, and so on, right? So mu n of x naught is equal to 1 over n delta x naught. So it's just like in the case of the periodic orbit, but here this is not periodic, right? So as you take n bigger and bigger, you're distributing it equally onto more and more points, right? Imagine that n equals 1,000,000. So if we now, imagine that we have n equals 1,000,000, so we have 1,000,000 points of the orbit. So each of these points on its own has a very small contribution to the measure, right? So 1 over 1,000,000 of the measure is here, 1 over 1,000,000 here, 1 over 1,000,000 here. And we still have, exactly like we did here, right? If we take some set A, this is the set A. So the measure of the set A is simply the proportion of points in here, right? If you have n equals 1,000,000, right? If n is equal to, say, 10 to the 6, 1,000,000, a large number, and suppose that 1/2 of those points belong to the set A, then the measure of A, according to mu n, when n equals 1,000,000, is 1/2, right? So when you look at that measure, it's true that each individual point has a very small measure, but of course there's 1,000,000 points. So the total measure in the system is still 1 kilogram of sand. It's still 1, right? It's just that this measure is very spread out. And then our question is, what happens as n goes to infinity? Right? That's what we're trying to do. We're somehow trying to look at the limit, in a sense, right? So what happens as n goes to infinity? And in particular, what this means is, are there any limit points, right? So we have a sequence. So does the sequence, so we have a sequence of probability measures. And we really want to know whether this sequence has limits. What do these limits mean? Does this sequence converge? These are the questions that we're going to address, right? What does this tell us about the dynamics? What does it mean for the limit of this sequence? In what way does it describe the asymptotic behavior of the orbits? Is it connected to the omega limit set? These are the questions that we're really going to address in this part of the course. Okay? So the first thing is, of course, what do we mean by limit? So to talk about limits, you need a topology, right? And you need a topology on the space of probability measures, right? So the natural topology, which again I presume you would have done either in the real analysis or in the functional analysis course, we consider the so-called weak star topology. This is called the weak star topology. So the kind of fancy description of this is that the measures are linear, they're the dual of continuous functions, so they're linear functionals on the space of continuous functions, and so the weak star topology is induced by the topology on the dual of continuous functions, but a more direct, basically this means something quite easy, which is that a sequence of probability measures converges to mu. The definition of convergence, to describe the topology, really we need to say what it means for a sequence to converge, right? So for two measures, two probability measures to be the same. And this converges if the integral of d mu n converges to the integral of d mu for all phi continuous on our space, right? So all phi x to r, which are continuous functions. So given an infinite sequence, we have this notion of convergence. So the question is, does the sequence converge? If it does not converge, does it have some limit points, right? So the question is really, does the sequence mu n have, in particular, a unique limit? What do these limit points say about the dynamics? Any questions? So we'll start by looking at some examples. Okay, so some very simple examples. And then we will look at some more intriguing examples.
Professor, our space is compact or not?
At the
For
moment,
example,
yeah.
what? Compact? Is it compact? For example, this space of all measures is dual of continuous functions on compact set. Like, is it compact or not? Consider it.
So as we shall see, if the space is not compact, then this sequence might not have any limit points. Right? So you are correct in emphasizing that the compactness of X plays an important role. Let's look at some examples. If the space is compact, then by general theorems of function analysis, the space of probability measures is also compact in the weak star topology, which means that any infinite sequence must have some limit points, even if it does not converge. Right? If it is not compact, as we shall see with some very simple examples, it does not necessarily have any limit points. So let's look at one example, first of all. simple example. Suppose that we have a situation where fx of 0 converges to a fixed point. Like in, for example, if f is a map of the unit interval, and the simplest examples that we looked at, right? Like 1/2 of x, these simple examples. So, so what happens? So I will leave the actual calculation, the proof to you as an exercise, but it's quite simple. So if you take some initial condition x0, as we saw before, this maps to x1, this maps to x2, and we have this infinite sequence converging to 0. So from an intuitive point of view, let's think of it just intuitively, what is happening to this family of measures, mu n of x0. Remember, this is 1/n sum of xi. So what is the measure of various sets here, right? So if we take a set A here, suppose I take an interval A, right? Then this interval A only contains the point x0. So the measure mu n x naught of A, this is a measure, mu n of x naught, right? Mu n of x naught of A contains only one out of n of these points, so the measure is exactly 1/n. So as n increases, this measure gets smaller and smaller, and the measure of A tends to 0 as n tends to infinity. Right? So what's happening is that this measure, this property, is describing the fact that this orbit never comes back to A, right? So in the set A, we have one point of the orbit. At every finite stage, this point has some measure because we are distributing the measure evenly along the first n points of the orbit. But this measure becomes less and less as time goes by, right? And of course, this is true even if we take any interval, subinterval that does not contain 0, then this interval will contain some finite number of points of the orbit. It may even be 1,000,000. That's okay. So that means that this set A has measure 1 when n is less than 1,000,000, right? Because when A is less than 1,000,000, as we said, initially all the measure is in x0, then we distribute it equally on these points. As long as A contains all the points, it will have measure 1. But then, when n gets sufficiently big, we will start losing a bit of measure of this set A, right? Because the points will start coming out here. And then, when n gets sufficiently big, the measure of this will still go to 0. So all the measure is being pushed towards 0, closer and closer to 0, right? So if you take a set B that contains 0, so let's suppose we take another set that contains 0. So if B is equal to the interval 0 epsilon, or any epsilon, then when epsilon is very small, and n is small, the measure of B will be 0. Because until the orbit has not yet entered B, this B will not see any measure, right? But then, eventually, the points of the orbit start entering B. And then, of course, when n is sufficiently large, most of the points will be inside B, right? And this will become more and more. So as n tends to infinity, the number of points that are outside B will stay the same because it does not change. Okay, once I fix epsilon, I know that I have 1 million points outside B, but then all the others are inside B, right? So as n becomes sufficiently big, the proportion of this 1 million points over n goes to 0. So the measure that stays outside B goes to 0, right? And all the measure tends to this. So the measure mu n of B tends to 1 as n tends to infinity. So the measure is accumulating in smaller and smaller neighborhoods of the point 0. And this is true for any epsilon sufficiently big, okay? So it will not be a surprise, intuitively it's fairly clear, that what is happening here is that this sequence of measure is converging to a measure that is really just sitting on B, right? Because however small epsilon you take, the interval outside B, the measure will eventually go to 0, right? So, so what happens here, okay, let me write it as a little lemma, which is just an exercise, which is that mu n is converging to the Dirac delta in 0 as n tends to infinity. And this is fairly easy to prove using the definition of the weak star topology. I will not do that. I wanted to give you here a feeling, you know, to see what is actually happening. But it's very easy because if you think of a continuous function, okay, I will let you do it. If you think of these measures and the weak star topology, okay, it's a little exercise, but you can prove this formally, okay? So I will leave this actual proof as an exercise. But it's really just a question of formalizing this idea that we have here. Okay, so you can see that this is true whenever, this is not just in this case, whenever you have, for example, if you have a contraction in any case, if you have f x to x is a contraction map, okay, remember this means that there exists a unique fixed point and every point converges to a fixed point. If it's a contraction, okay, then this implies that mu n of x0 converges to the Dirac delta in P for all initial conditions in your space, right? So every initial condition you choose converges to this fixed point P, and so we have this kind of convergence. So this is very consistent with the omega limit, right? This is the omega limit also of these points is P. The measures converge to delta P. It's all very simple. Before we look at some more interesting examples, let me point out this question about the lack of compactness. The lack of compactness. So of course, if we take x is the open interval 0, 1, right, and we take the same map f of x equals 1/2 of x, then you can see that you're still trying, this is the open interval, right? And you look at mu n of x naught, the only limit that it can converge to is delta of 0, because if you take any neighborhood of 0, any interval that does not, every interval, so every how should we say this? So every interval, for any interval, any closed interval AB, so we have that mu n of any closed interval AB tends to 0 as n tends to infinity, right? Because any closed interval cannot contain 0, and so eventually all the points, eventually the proportion of points that is outside this closed interval will grow unboundedly, so this will have 0. So the only possible measure that this sequence is trying to converge to is the Dirac delta in 0, but the Dirac delta 0 is not a measure on the space, right? Because 0 is not included in this space. So this is an example where this sequence does not converge, does not have a limit, does not have any limit points. Okay? Okay, so now let's look at some examples that show that the situation is more subtle than it is in the topological setting. And I think we will do that in the setting of our favorite map, which is 10x mod 1. Okay, where there is a richer actually, sorry, just one more simple example here. I will also write as an exercise. So if x0 is periodic, okay, I will leave this as an exercise. Let me not mention it. It's clear that if x0 is periodic and you construct this sequence of measures, mu n, then they will converge to that measure that we constructed right from the beginning for the periodic point. So it will converge to the equally distributed measure on the periodic point. So let's call this example 2, example 3, sorry. So now let's consider f of x equals 10x mod 1. Now, the situation becomes much richer here. So we know that we have fixed points. So can you give me an example? So remember, we're going to do a very similar thing than we did in the topological part. You remember we investigated this map and we tried to construct, using the decimal expansion, we tried to construct points that had different properties, fixed, periodic, pre-periodic, dense orbits, and so on. We're going to do something very similar, but we're going to be thinking of this sequence of measures. And trying to understand what happens to this sequence of measures for different points. Right? So maybe I forgot to say, I was about to say this for periodic point, but I didn't say for fixed point. If x naught itself is fixed, right, then it's obvious that xi is always equal to x naught. So this is just always delta in x naught. So this is the average of this delta in x naught. This is just equal to delta in x naught in the fixed point, right? So if x naught is a fixed point, this situation is trivial. Mu n is just always delta in x naught, and there's nothing really to prove. If xi is periodic, then there's some subtleties, but it converges to the obvious measure on the periodic point. If it converges to a fixed point, as we just saw, then this will converge to the Dirac delta on the fixed point. So here we don't really have any points converging to x0, right? Z0 is not a delta 0, so f0 is a fixed point, but it's not an attracting fixed point. So does there exist a point such that mu n of x0 converges to the Dirac delta in 0? Or at least such that some subsequence, right, such that there is a subsequence of mu n, so that this delta of 0 is in some subsequence. What do you think? Can we construct an orbit where the orbit spends a lot of time near 0, right? That is what this picture, this intuitive picture I described, is to do with there's lots of points on the orbit near 0, if we want this to have this as a limit point. How would we do that?
Zero point 1111.
0 point 1111. So 0.1111 is itself a fixed point. Right? So this is a fixed point. So for this fixed point, the Dirac deltas, so mu n of 0.1111 converges to just the Dirac delta in 0.1111. Right? In fact, in the case of a fixed point, mu n of 0.111 is always equal to the Dirac delta in that point for every n, so in particular it converges to that.
One weird example, I think x not just equal to 0, then it's just constant sequence, this sequence of measures. All of them equal to delta naught. If x not equal to 0.
Sorry, I didn't understand your suggestion, Mokshan.
If x not equal to 0, then it's fixed point, so all measures on all this sequence, it's constant sequence. Mu n is constant sequence, just, or my second suggestion, just we find some sequence, some initial point, its orbit, forward orbit converges to 0.
A point whose decimal
First suggestion
expansion
is just
eventually 0.
Sorry, Junaid, what are you saying?
A point whose decimal expansion is eventually 0.
Is eventually 0. Is that what you meant, Mokshan?
My first suggestion is just x0 equal to 0.
Okay, yes, clearly, yes. So
weird example, very stupid example.
No,
Second,
it's not stupid. It's a trivial example, but you're right. So, of course, there exists x0, which is 2, which is this fixed point 0. Okay, that's correct. So one example in which mu n converges to delta 0 is if you take x0 equals 0. Then another example, exactly as Junaid said, is that if you take any sequence 0, 5, 1, 2, 8, 7, and then eventually 0, right? So if it's eventually 0, then it is a pre-periodic or pre-fixed point, right? So it's a point that moves around and then it lands on 0, right? And then it is easy to see, it's a very similar, in some sense it's an even more trivial situation than this converging to 0. it's a combination of this, the fixed point, and the fact that this is prefixed. So it will, at some point after that, it will just be 0. So that's correct. Mu n of x0, in both cases, if you take x naught equals 0, if you take x naught, which is a pre-image of 0, that's what this means, right? This means dynamically that it's a pre-image of 0, then this will also converge to delta 0. That's absolutely right. Now, can we push this further and make it more interesting and have a point that is not a pre-image of 0, but where these sequences converge to 0 or have a limit point 0?
You can take 0, 1, 0, 0, 1, 0, 0, 0, 1, and so on.
And what is that doing? So your suggestion is x naught equals 0 0.1, 0, 1, 0, 0, 1, 0, 0. Is this your suggestion? Is that Eunice speaking? Yes? No?
Yes, that's my
Eunice.
suggestion.
Yes. So why is this, why do you think that this is kind of having some sequence or subsequence of these measures going to delta 0?
After a certain term, like it's gonna have 0, 0, 0, 1. It's gonna start with as much zeros as you want.
That's right. So try to articulate your thought better, Eunice. So what then? What is that going to give? Why does that heuristically work?
I think it contains all finite blocks of 0.
Excuse me, Mubarak, say again.
It contains all finite blocks of zeros.
It contains, that's right, it contains arbitrarily long blocks of zeros. So here we have 4 zeros and so on. So what this is saying, so you're correct. This is a correct example, right? So what this is happening, this is not eventually periodic. It's not eventually fixed, right? It never repeats. It does not converge to 0 because, there will be some arbitrarily large iterates in which xn will start with 0.1 something, right? So you will, and infinitely many times, you will find yourself close to 0.1. So this is important. So the sequence of iterates, if you look at the orbit, if you look at the forward orbit of x0, it does not converge to 0, right? Because xn is close to 1, is close to 0.1 infinitely many times. In fact, 0.1 is in the omega limit set, right? Because you take, it is getting closer and closer. Every time here it's 0.10 something, then here it's 0.1001 something, right? With 0.100001, so it's getting closer and closer to 1. But, and this is where your observation is precisely correct, right? So the amount of time that is spending near 0 is much bigger than the amount of time that it is spending near 1. So if you now look at, depending, if you take a subsequence that starts with zeros, here we'll get 0.4 zeros. Then you get, if you wait long enough, you get 0.1000 zeros, right? And then a 1, which means that you're extremely close to 0. And then if you wait, and then you stay close for a very long time, right? Because you have 1,000 zeros. When you multiply by 10 again, you will shift by 1 decimal place and you will still get 999 zeros. So you're very close. And at some point you will get xn equals 0 point and you have 1,000,000 zeros and then a 1, right? So you're extremely close and it will take you a very long time to move away from that position, because if you have 1,000,000 zeros, then after one iterate, you still have 999,999 zeros, so you're still very close, and it will take you a long time before you get, but after 1,000,000 iterates, you will then jump all the way to here, right? At some point, you will get 0.01, and then you will jump to here, and then the next thing you know, after this, you've jumped once to here, close to 1, and you will jump very, very close to 0, and then you will spend a huge amount of time near 0. Okay? So I think it should be possible to prove the following thing that I will leave as an exercise. So I think that the limit set, now this I'm not 100% sure, I confess, but I think we have that the limit, omega limit set is equal to the 2.0 and 1, because it is also accumulating 1. I don't think there is any other point in the limits, or maybe, no, maybe it also...
0.01.
Yes, you're right, you're right. So it contains, the omega limit set contains 1, 0.1, 0.01, and so on. It contains this infinite set of points, 0.001, that's right, and also the point 0. So it contains the point 0, the point 1, and then all these points here. Okay, so it is this countable set. And
1 is the same as 0. It's mod 1.
sorry, not 1, I meant 0. Yes, thank you, thank you. So I meant 0.1, so 0.1, 0.1 I meant, yeah, this point here is in the limit point, and then all the intermediate points. And now for these measures, I would say, to be honest, I'm not sure if it converges or not. Again, what we can say for sure is that there exists a subsequence such that mu nj converges to the Dirac delta 0. Okay, and I will leave this as an exercise, but this is very simple because basically you can take a subsequence that converges to 0, right? And then you apply exactly the same calculation that we did in this case. It's just, it's not the full orbit does not converge to 0 because the omega limit set contains all the points, but there is a subsequence that converges to 0, and therefore for this subsequence, this converges to delta 0. Let's push this idea a little bit further, okay? So how about now we construct a point that has both, we want an initial condition such that some mu n, some subsequence converges to delta 0, and some other subsequence converges, say, to the fixed point. So there is a fixed point, okay, 0.111. Delta in 0.111, or any other fixed point. How do we construct this? Well, we can follow the similar principle, right? What was the principle of this example was that you have a large, that you have I'm trying to think. So I think the intuitive idea that all you need is a converging subsequence to get this is not correct, right? Because here you can also find a subsequence. Topologically, you can find a subsequence. So the omega limit set contains these points, but you cannot find a subsequence converging to these points. So you need not just a subsequence, but you need the proportion of points close to 0 to get larger and larger, right? So if you look now at the first 1,000 digits, then in some sense it's because the proportion of zeros in the first 1,000 or 1 million digits becomes bigger and bigger, right? It tends to 1. In fact, the proportion of zeros tends to 1. I think that will prove that this actually converges, not that it's just a subsequence. But in this case, so what we need is to have larger and larger blocks, both of 0 and of 1, right? So here we can take 0.01, 00, 11, 000, 111, and so on, and we can do something similar. And then if you look at the proportion of zeros and ones, this is just an intuitive thing, right? So to prove this, you really need to prove it using the definition of weak star limit, okay? But intuitively, it's really about the fact that you have arbitrarily large blocks of 0, and these very large blocks of 0, they occur for a positive proportion of time. So when you look at the first 1 million iterates of this point, you will see, and if you take a small, you really follow the same similar logic to what we used there, okay? So if you take very small neighborhoods of zeros and ones, after some large, when n is very large, you will see that you're spending a positive proportion of time in here and a positive proportion of time in here, which means that there is mass. Positive proportion of mass means positive proportion of sand, right? If you have a billion iterations and half of them are in this small neighborhood, then the measure of this will be half, right? Mu n of this will be half. And if you take a smaller neighborhood and you wait longer enough, and you see that when you wait long enough, half the measure of this will still be uniformly positive, then you know that you're getting delta 0 as a limit of this subsequence here. Now let's take one step further and let's see if we can actually really completely mess with the omega limit, and this is what I call somehow the statistical limit. So suppose I take x0 has a dense orbit, right? Suppose I take x0 such that omega of x0 is equal, is the whole thing, is 0, 1, right? Remember that we could do that by just taking all finite blocks, right? 0.012 up to 9, and then we did this construction. So what can we get? Or rather, let me ask a more specific question. Can we modify this? Okay, when you look at it like this, it's not completely clear where it's spending a lot of time. Can we modify this in such a way to guarantee, so can we guarantee, can we modify, can we use this, or rather, okay, so maybe I want to say something different. I don't want this particular example. I say, does there exist x naught such that this is dense and such that there is some sequence mu nj that converges to delta zero. How do we do that? We want to construct this example, and we can start, this is what I was doing before, but I should have mentioned this before. We can start with the orbit which is dense, right? We can start with some x naught equals 0.0129 and so on, this orbit that is dense. And then how do we modify this to guarantee, I realize, so let me be clear that I realize I'm not giving you proofs of this fact, right? I'm relying at the moment in the exercise, I will show you how you prove these facts. At the moment, I'm relying on constructions that are intuitive, right? And are based on the observation that I made before, which is that if you look at 1,000 or 1,000,000 pieces of orbit, then there will be a large proportion in the neighborhood of that point, right? So when I say that there exists a subsequence converging to delta zero, I'm saying, okay, I want to take a point and I want to iterate this point 1,000,000 times, okay? And I want to, or 1,000,000,000 times, okay? And I want to make sure that when I iterate these 1,000,000,000 times, half of the times I'm in a very small neighborhood of zero. And then when I iterated 1,000,000,000 times, still half of the times I am in this very small neighborhood of zero, right? So I want to repeat the situation that I had before for this. So let me maybe at this point, because I realize we've gone late and we haven't had a break, let's just have a short break, yes? So it's 5:08. Let's just take a 4-minute break just to get a glass of water. And I'll meet you again in 4 minutes, okay? So then we can complete this section. So back to our problem here, we can use exactly the same strategy that Younes proposed for the previous map, right? What was that strategy? That strategy was to have increasing blocks of zeros. So if you remember, we made this comment that what you need for an orbit to be dense is you just need it to contain all finite blocks of digits, right? But of course, it can contain lots of additional blocks and repeated blocks, right? As long as it contains all finite blocks. So if we now take this particular point, I can swap these blocks around, or I can just, in between the blocks, I can add big blocks of zeros, right? So here I can put a 0, and in fact, in between the 1 and 2, I can put 2 zeros, and so on. Here I can put lots of zeros, right? In between every single block, if I want, or whatever, I can put 1 0, then 2 zeros, then 3 zeros, so that I still have, then here I will put every 2, I will put lots of zeros up to here, right? And then every 3, because these are blocks of 3, so then here I will put lots of blocks of zeros, okay? So that the proportion of zeros is increasing all the time. So if I look now at the first 1 billion iterations, I may have 90% of those digits as 0, which means that I spend 90% of the time very close to 0, right? Because 90% of the time I will have 0.000 something. And then because I'm putting bigger and bigger blocks of 0, if I take 1 billion iterations, then maybe I'm even spending 99% of the time here. But the orbit is still dense. Right? So the omega limit is still the whole interval 0, 1. This is a fundamental example to appreciate, in some sense, the difference between the topological limit set given by the omega limit set and the measure theoretic limits given by the limits of this sequence of measures, which may give you completely different pictures because we're looking at the orbit from a completely different point of view, right? In the first case, when we look at the limit points, we're just looking at the limit points. We don't know how often you come close, right? We say, okay, if I take any points here, I can find some subsequence of the orbit that converges to point Z, okay? But if I take a neighborhood of Z and I say, okay, if I now look at the first billion digits, first billion iterates, what proportion of this belongs to Z? This proportion may be going to 0 as n goes to infinity. Okay. Instead, if I take a neighborhood of 0, I still have that 0 as a limit point, and if I look at this neighborhood and I say, okay, I take 1 billion iterates of my initial condition, which proportion of these iterates belongs to here, then I see that this is actually very large, 95%. If I wait any longer, it might become 99% because the proportion of zeros is becoming more and more larger in this sequence, right? So this, sequence of measures is really looking at the statistics of the orbit. That's why it's called the statistics. It is taking into account how much time the orbit is spending in different regions of phase space. Okay? This is really the fundamental. So this lecture here is really not so much of a technical or statements, but it's trying to just emphasize these different viewpoints and the different characteristics of the dynamics that they are looking at. So in this case, I think by doing the procedure that we have here, we actually have that this converges to 0 because you actually get that the increasing proportion of time tending towards 1 is a neighborhood of 0. Now you can easily, however, split that up and do the same thing that we did before. Now I put not just sequences of ones, but sequence of zeros. So everywhere I had a 0, I put 0, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 1, and so on, right? So I still have exactly this infinite, this dense orbit because I have all finite blocks. And now, however, if I look the first billion orbits, I don't get 99% zeros, but I get that this 99% of the digits is equally shared between sequences of zeros and sequences of ones. So in fact, I get that out of these billion iterates, almost half the time is spent near 0, and almost half the time is spent near 1, right? And when I go even further, it will be more than half the time. So the proportion of iterates of the orbit that are very close to 0 and very close to 1 tends to half and half, right? So in this case, we will get one subsequence converging to 0 and one subsequence converging to delta 0.0111. But the orbit, the omega limit set is still the whole interval 0, 1. Any questions? Okay, so before I finish, I will give the one final definition today. I want to emphasize the peculiarity of this kind of situation. What does it mean? So let me write it like this. So if the conclusion, a little bit of our conversation, is that if mu n of x naught converges to some mu, to some probability measure mu, okay, then we can say that mu describes, in some sense, the statistics of the forward orbit of x0, right? Because if mu n of x converges to some mu, this means that when n is very big, this measure here, which is equally distributed along all the points, is approximated by mu, right? Or mu approximates, this measure approximates mu, but it's the same thing to say that mu approximates this measure if you want, if you fix some very large n. So what that means is that because this measure tells you exactly where the points live, right? Because this measure exists, is equally distributed along this finite orbit, and it is very close to this measure, then if this measure has, you look at the measure mu on your space, and if this measure A has mu of A equals 1/2, right? If you know this measure mu, then you know that when n is very big, half of the orbits, you take some initial condition, half of the orbits will be close to the set A, at least, right? Because mu nx of the set A will be close to mu of A, essentially. Now, what happens, however, when it does not converge? If mu n does not converge, by does not converge, I mean it has more than one limit points. It has different subsequences, right? We have mu n of x, mu ni of x0 converges to some mu, and mu nj converges to some different measure nu, as in this case where you have this converging to delta 0 and this other subsequence converging to the fixed point. Sorry, not point 1, this is point 111, right? To this fixed point. Now, what does this mean? This is very interesting and very subtle, okay? But I think this is a crucial point. What does this mean? This means that if I look at the orbit of x naught, and I look at the distribution of the points, like the statistics of the points at these moments, at this particular sequence of moments, this statistics is described by the measure mu. But if I look at the statistics of the orbit at a different sequence of times, this statistics is defined by a different measure, nu. So what this means is that what you see, the statistics, depends on the time scale that you're looking at, right? Because you can think of these sequences as different time scales, right? In general, these would be very different. So imagine this example, I think, illustrates very well. Imagine that I'm tossing a coin, right? As we know, tossing a coin, you might get 5 heads initially, even 10 heads, although it's very unlikely. But if you toss it long enough, you will converge to a measure that is half heads, half tails, right? And the more coins you toss, and the closer you will get to half-half, okay? This corresponds pretty much to this situation. The statistics is converging to something, okay? Now, what is this kind of picture in terms of tossing a coin? This says that the statistics is not converging to something. Different timescales, you see different things. So for example, suppose I say, okay, if I toss the coin a few hundred times, I get 90% heads. But if I toss it a few million times, I'm on a different scale, I get 90% tails, right? But if I toss it a few billion times, because this is, say, 1 billion, then the statistics look like this, and I get 90% heads again. And it keeps oscillating like this, right? So depending on how long you look, it looks like the statistics is like this, but then if you look longer, suddenly it looks like the statistics is like this. So this is very different from the omega limit set, where you happily have many different limit points, and in fact you want to describe the orbit in terms of these limit points. It is completely different, because here you are talking about measures, and if the measure converges, now this measure does not need to be a measure that is just sitting on a fixed point or periodic orbit. As we shall see, in some cases it will be Lebesgue. For example, you may have some cases in which this sequence converges to Lebesgue measure. And if it converges to Lebesgue measure, it means that if you look at 1 million iterates, these 1 million iterates are very uniformly distributed in your space, okay? But if it converges to Lebesgue measure, and you take very large n, this will be very close to Lebesgue measure. If you take an even larger n, it will be even closer to Lebesgue measure, right? So the statistics you see are consistent across timescales. Whereas if you do not have convergence, then the statistics you see are not consistent across timescales. Okay? Just to emphasize this point more, for those of you who are interested in applications of dynamical systems to science, it is almost one of the dogmas of scientific research that you can do statistics on a sample, right? And you generalize, you rescale that sample to the whole population. For example, when they take polls, and they say 60% of the population is going to vote for this party, or 60% of the population think is this, they don't, of course, ask the whole population, right? They take a small sample that they think is representative, and in that sample they find 60% of the population. Or if you do a scientific experiment and you are looking at how many insects are in some ecosystem, and you take a small region and you find 10% of this insect, 10% of the other, and then you extend it, somehow you generalize, right? So there is a kind of sense that these statistics are invariant across different scales, right? And these simple mathematical examples show that you have many situations, mathematically natural. You can construct, in this system, we can construct many different orbits in which the statistics is not consistent across scales, right? In which the statistics, as soon as you have that this has several limit points, it means that the statistics is not consistent against scales. So let me just finish with this motivation. We define, so let mu be a probability measure. So, and then we define something called the basin of mu is precisely the set of points such that measure mu n, set of points x naught, such that mu x n of naught converges to mu. Okay, so the question that we really want, so the conclusion of all this discussion, the kind of, in some sense, where I wanted to arrive at the end of this discussion, is that when we look at some initial condition here, right, and we define this sequence of measures mu n of x0, what we really want is to show that this converges to something. In other words, lack of convergence is in some sense a bad situation, right? So we would like to show that this converges to some measure mu, is the question, does it converge? And what we would like is say, okay, if this converges to some measure mu, and we take another initial condition, is it possible that this initial condition also converges to the measure mu? Do they both converge to the measure mu? And these are the questions that we're going to tackle. And so one way to do that is to define this notion. We take the measure mu, and we look at the set of points for which these averages converge to mu. This may be empty, there may be no measure. If I now just take an arbitrary measure, I may take the Dirac delta on some point here. There might be nothing that converges to that. And then we say, and we're particularly interested in measures mu in which the basin is big, okay? So if X is more than a metric space, so if X is an interval or a space, a Riemannian manifold, where we can define the Riemannian volume or the Lebesgue measure on this space, then we say that mu is a physical measure if the Lebesgue measure of the basin is positive. So the way I'm going to focus this last part of the course is on the problem of the existence of physical measures, right? So this whole discussion is aimed at introducing the meaning of looking at orbits from a statistical point of view, the importance of convergence as opposed to having many different limit points. Of course, it's a question of taste, which one you like best. In effect, there's a lot of very interesting research and very interesting study of these situations where you have many limit points, and so the dynamics, the statistics depend on the different time scales. But the point of view we're going to take in this course is that a system is well behaved if for most initial conditions this actually converges. We'd like to know for which systems and for which initial condition this converges. And in particular, of course, we're interested to know if there are many points that converge to the same measure. And what that means, by many points, we mean a positive Lebesgue set of points. So we're interested in the problem of saying, given a dynamical system, does there exist a physical measure? So does there exist a measure such that there is a positive Lebesgue set of points in the basin, which means a positive Lebesgue measure set of points that converges to this, right? And there is a well-known conjecture called the Pallis Conjecture, which has been guiding a lot of research in dynamical systems and ergodic theory for the last several decades. And this Pallis conjecture says that for typical dynamical systems have physical measures, and in fact have a finite number of physical measures, and the union of their basin has full Lebesgue measure. So this means that for typical dynamical systems, almost every initial condition converges to one of a finite number of measures. In particular, it converges. This is typical. For typical systems, there are lots of counterexamples, so it requires specifying what we mean by typical systems, because there are examples of systems that have no physical measure. If you think about it, the identity map is a typical example. I will put that as an exercise. It's very easy to show that the identity map, every point is fixed, so every point just this converges to the Dirac delta in that point, so there's no point, there's no measure whose basin has positive Lebesgue measure. So there are simple systems that have no physical measures. There are systems which have infinite number of physical measures, but there is some work, a lot of work in this direction. And anyway, it really just points to the general direction of the question of the existence of physical measures in systems. And that is what we're going to study in the remaining part of the course. Okay, any questions before we finish? Okay, so thank you very much. Bye.
Thank you. Bye.
Thank you.
Thank you.
Thank you.